Okay, so, let me say a couple words about, well, welcome to the last homeowner. We talked about word fields last time a little bit. Show that the real numbers, and we're fixing to take a close look at the real numbers and do some kind of basic stuff. That is sort of set up for calculus in a certain sense. But show that the complex numbers is not an ordered field. And I'll give you a hint on that one. If it is, then I, the square root of -1 is either positive or negative. See if you can get a contradiction from that. Number two, you find this, at least in the appendix of a good calculus book, actually. Let S be a non-empty subset of R and F from S to R, a function, and A, an element in R. Additionally, we will assume that F is defined on an open interval containing A, except perhaps at A. We say that the limit of f of x as x goes to A is L, and we write it in the form that I'm familiar with. If for every epsilon bigger than 0, there's a delta bigger than 0, such that x minus A is strictly between 0 and delta, implies f of x minus L is less than x. How many of you have seen that definition in the calculus time before? Good. Yeah, it's a shame because I think a lot of times you don't. This is what's called precise definition. The limit in any good calculus, it'll be a section. If you had AP or some other calculus class, you might have actually skipped that section, but it'll be in there. This is the precise definition of the limit. Use this to show a couple of limit laws. Show that if the limit of as x goes to A of f of x is L, and the limit as x goes to A of g of x is M, and the limit as x goes to A of f of x plus g of x is, surprise, surprise, L plus M. And B, do the product function of this. If the limit as x goes to A is L, the limit is g goes to, or x goes to A of g is M, show the limit as x goes to A of f of x times g of x is L times M. And finally, number three, you all remember the squeeze theorem perhaps. If f, g, and h are functions defined on an open interval I containing the real number A, except maybe at A, they might, any of those functions might not be defined at A. And f of x is the little one, h of x is the big one, and g of x is always squeezed between there. For every x in this interval, except perhaps at A. If the limit is x goes to A of f and g, so if little guy and big guy both go to L, the middle guy has to go to L. This is squeeze theorem. Use the definition from number 2 for what it means for limit exists to prove the squeeze theorem. This is actually not hard. This is actually not too hard. But it will require you to think this way, and I think that this is a good stepping stone in the kind of things that you might encounter in 4530 or real analysis, whatever you take. So notice there's not too many problems on this one, so hopefully it won't be too bad. And let me say something about share. As you know, I sent y'all some email this morning. I've got to be out of the office for a kids' exam from like 11:10 until I'm gonna get back as quick as I can. I should be able to get back by 12:30. Next week, the last week of classes, I will have usual office hours on Monday and Wednesday. I will not Friday. You'll have a substitute on Friday. I'm gonna be in Kentucky giving a talk. I will be back for the math end. Please be at the math end, take advantage of this resource. I put in a request for us to have a review session Tuesday night. I will have my regular office hours Monday and Wednesday. I mean, and Friday too, but after your exam. Monday and Wednesday at the regular time, and then probably some extra. And I'll probably be around Tuesday too. So if you have any requests or need to see me, let me know. Okay. Any questions so far? Okay, so we're doing some stuff here. So I want to kind of tie up some loose ends, maybe from the old calculus class you had. Okay. You all seen this at one point, although maybe you don't remember. remember what a sequence is. What does bounded mean? It means that there exist two numbers, floor, ceiling, such that so every one of these numbers is bigger than F, bigger than or equal to F, and every one of them is smaller than or equal to C. Floor, ceiling, all the numbers in this sequence are clean here. What does monotonic mean? Well, from the Greek, mono, one, tonic, tonic. It just means it does one thing. So either you're always going up or always going down. Let's assume that our sequence is always going up. And this is A1, A2, A3, A4. Now, the sequence is bounded, so it always has to squeeze between floor and ceiling, and it's always going up. So if I continue, it might look like this. It can never get above the F, and it's always got to be going up. So this sequence actually must converge intuitively, right? And what it will converge to is the lowest possible value for, in this case, well, apparently things are upside down, but it's supposed to be floor. But it'll be the lowest possible value for the ceiling in this case, right? Intuitively, this works, right? But actually, this is the fact that this is true is really requires some subtle properties to rely on. Let me give you an example. Look at the sequence here. The first term is 1, 6, 9, 8, the third is 1 plus an 8, 1 plus 7. What I'm doing is I'm summing the first n cubes. Well, first n reciprocals. Everybody agree with that? This is monotonic. It's increasing. Because at every successive step, I add up something new positive to it, so it's getting bigger. Do I agree with that? It's also bounded. That might be a little bit less clear. You might explain why it's bounded.
It's never gonna be less than one.
Oh, that's right. Okay, so I was pointing out that everything is always at this one. Okay, how about a ceiling though? That's a little stickier, right? It does have a ceiling. I'll prove this for you. Well, I'm gonna go in terms of secret. Um, let me draw you a picture of what this looks like. Uh, So. This is two, yeah. Let this be one over A, one over, I should make this bigger. Yes. 1.8. 1.7. 1.64. So this is the point here, 2.18. This is the point 3, 1.27. This is the point, I'm sorry, 1.8. 2.7, 3, 1/64. And so. It's all off here. I'm sorry about this. I need to fix this. Let's look, let me start here and look at some boxes here. So we 1, 2, 3, 4, 5. Okay. One. This is 2.8. This is 1.3, 1.7. 4, 1/64, etc. So if I sort of connect these dots here, what function would I have here? See the pattern of points here? That's right. I agree with this. So let's make some boxes here. I'm going to make some boxes that look like this by connecting the right-hand endpoint of every interval like this. So on. So the width of this box, for example, is 1, and what's its height? 1/8, right? So the total area should be 1/8. Right, agree with that? The width of this box is 1, and the height is now what? 1/27, right? Width of this box is 1, and the height is 1/64, and so. Now, let me point out that let me ask you this. Which is bigger, the area under the yellow curve from here to here, or the area under the boxes here? The yellow curve's a little bigger, everybody agree with that? Because there's always a little left over and we never go under the boxes, right? So this thing should be less than or equal to limits, please. Well, I just want to find out many so far. Right. right? So for example, 1/8 is less than or equal to the interval from 1 to 2 of this function. 1/8 plus 1/27, the interval from 1 to 3, 1/8 plus 1/27.6, fourth interval from 1 to 4, etc. Everybody okay with it? So let's go back to our SN here. It's less than or equal to 1 plus the interval from 1 to n of 1 over x cubed dx. The only thing that's different from here to here is I just put an extra 1 here. Both sides. 1 here. And this is less than or equal to 1 plus the interval from 1 to infinity. Because the interval from 1 to infinity of this is certainly bigger than the interval from 1 to n, because this function is always positive, right? This is equal to 1 plus the antiderivative of this is minus 1 over 2x squared, evaluated from 1 to infinity, which is, that's going to be 0 minus a half. So every term of this, there's a sigma, 3 halves. So this sequence actually is bounded. As Alex pointed out, it's less than or equal to 1, or it's greater than or equal to 1, less than or equal to 3 halves. Right? Right, okay with it. And the sum of the, and actually, what is this sequence? What's the limit of the sequence? These are the partial sums, so it's actually whatever the sum is. So basically, I know that this sum converges because it is the limit of the sequence of partial sums. But here's the point I'm trying to make. I know this works because it's a bounded monotonic sequence. It converges to something. Nobody knows what. So, in other words, if I had 1 over n, if I took the sum 1 over n squared, that adds up to I think it's pi squared over 6. And if this was 1 over n to the 4th, I think it's pi to the 4th over 90, something like this. 1 over n cubed, nobody knows it close to that. You can estimate it really well, but you don't know. So there's a bit of magic to this theorem that a bounded monotonic sequence always converges. In fact, in this example, we know it converges to something. We just don't know exactly what that something is. So let's kind of tackle this. How many of you have ever heard of the notion of compactness? Anybody? Right, other than a parking space, right? What does it mean? What do you think about when you hear the word compact? Small, tight, something like this, right? And that's loosely speaking, that's what compactness means. Compactness, even though you've never heard it, is an extremely important concept, and you've even seen it in calculus. Does anybody remember what the extreme value theorem is? It's something like, if you have a function that is continuous on a closed interval, then it attains its maximum and minimum somewhere in that interval, right? They wanted the function, the continuous gives you sort of a boundedness for this on a closed interval. Really, what's important about that is the interval that you're on is what we call a compact interval. And in fact, this fancy word here for the real numbers, compact means closed and bounded. How many of you know what bounded we know? It means you can sandwich it in two things. How about closed? Have you heard of closed? If I tell you what a closed interval is, right, that just means it's got the endpoint, right? Well, there's a more general definition of closed that we'll explore, but first I've got to tell you what, before closed, I need to. Definition 721, but A and delta being an R, with delta bigger than 0. We define the delta neighborhood of A to be A minus delta, A plus delta. This is sometimes called the neighborhood of A, of length delta about it. And it is the set of all X and R, since the absolute value of X minus A is less than delta. If you look at your homework assignment, you will see, this is quite familiar, because this is part of my definition of one of the problems. Let me draw you a picture of this. This is all there is to this. You've got some point on the real line, we'll call it A. And you pick some delta. Delta's like a little measure, it's just like a little length. This is the point. A plus delta. Let's measure it off, right? This is the point. A minus delta. And the delta neighborhood is just all the stuff that's in between. Open, open. So the delta neighborhood is just this bit here. It's just the interval from A minus delta to A plus delta. Definition. So does everybody understand what this delta neighborhood is of A?
It's just a little interval around it.
Be a subset. Not empty all over wording, this will take care of this. A point X in this set is an interior point. Here, there exists delta is bigger than 0, such that the neighborhood X delta is contained at A. Okay, for example, let A be this set on the real line. Let's see if we can find this material. So A consists of these 4 dots and then this half open interval, right? Is this an interior point? No way, right? Because no matter how small delta is, there's crap that's in its neighborhood that's not an A, right? It's missing. In fact, none of these are interior points. And there's one more. One more point that's not interior. Basically, this.
The right boundary.
Correct. The right boundary's halfway there, isn't it? But no matter how small delta is, you're missing stuff on the right, right? That's bad. Right? Every other point is an interior. Because every other point in here, you can make delta small enough, so there's a little neighbor. So being an interior point is one that you're sort of inside the blanket, right? This one's bad because its toes are sticking out. These are bad because they've got no blanket at all. But all the stuff inside there, they're blanketed, they're covered up in a neighborhood by everything, right? Okay. So now what we know by interior point is it's completely inside the set in the sense that there's a small enough little delta around it so that everything in that neighborhood, so it contains a neighborhood point. Definition. You all have familiarity with open sets, or I'm sorry, open intervals. An open interval intuitively, that you probably dealt with, is just an interval from A to B that doesn't contain either of the endpoints, right? A set, A and R, the reals, is open. And in fact, you can define this more generally set. All points of A are interior points. Put it. That is, for all X in A, there exists delta bigger than 0, such that the neighborhood of X for small enough delta is contained in X. Everybody okay? So a set is open if all its points are interior points. That is, given any point in A, there is a small enough delta such that the neighborhood of size delta around X is completely contained, right? Can anybody name me an example of an open set that is not an interval? Right, because, so my first example that jumps to mind is, how about the interval from 1 to 2? That's an open set because every point in there is interior, right? Can anybody give me an example of an open set that doesn't look like that?
The so when it's changing is defined, I guess.
Right, but if it, oh, okay, yeah, the domain of tangent?
Yeah.
I like that answer. So his set, the domain of tangent looks like this. You go through and you remove every multiple of pi, isn't it? Or, I guess it's pi over 2 plus pi k, right? So what do? You take all the reals and you remove periodically these points. So I'm not putting the exact points here, but that's what it looks like, right? That's a great answer. That point, right? Any point in there is an interior point, if I agree with that. How about all the reals? Right? All the reals. That's not an interval, and that's an empty set. So is the empty set. Right? All points of A, there are no points of A, so this is vacuous and satisfied. Right? So empty set, reals, There's another one set. These are all examples of open sets, everything's interior. Yes.
I thought A, from like 7.2.2, A could not.
You know what, you can remove that actually, because like I said, when I wrote that down, I just said A is not empty and I don't really need that, because if you look at the definition. But yeah, thank you for keeping me on the toes. Okay. Well, let me finish this definition by, I'll do it this way. Definition 7.2.3 C. Anybody know what the definition of closed is? I know what a closed interval is, right? It's the interval with both the endpoints. They said it's said to be closed if when you remove the set A from it, you get an open set. So let's look at some examples of closed sets. What happens when you remove this? What happens when you remove that? So this is my typical definition of closed set, what I remember from calculus, closed interval. What happens when I remove that from the real numbers? What am I left with? Right, you're left with something that looks like this. Right? And this is open. Because all the points here are interior, right? So, so closed just means whatever's left over is open. That might seem complicated, but actually closed makes things a little easier. Here's another one. Cantor set, where you pulled out the middle 1/3, open, pulled out, and so really what it is it's the complement of none of the sets, so it's closed. I'm gonna tell you some stuff here that's gonna justify my statement that the Cantor set is closed. Of course, if I walk up to you on the street and give you a random set, it's probably neither open nor closed. So don't develop the prejudice in your head that, you know, if I give you a set, it's one of these two. It's not. These are special kinds of sets, right? Open and closed. Most sets are not, right? So for example, the interval from 0 to 1, where you don't include 0 but do include 1, is neither closed nor is it open, right? Because it's not closed because not all those points, or I'm sorry, it's not open because not all those points are interior, because you've got the point 1 at the end, and its complement is also not open. There. Set 2, 5. Let Xi be a collection of open sets, or I'm sorry, of sets. Number 1, here, each Xi is open, then the unit of Xi. Okay, this one's a big, this one's huge. What it says is that if you have any collection of open sets and you look at their unit, it's still open. 2, if each Xi is open and the index set is finite, then Okay, so what this first part says is, if you have any collection of open sets, their union is still open, no matter what. Number two says, if I've got finitely many open sets, their intersection is open. You might say, is this true for any intersection? The answer is no. I'll give you an example. If each xi is closed, then the intersection of xi is closed. And four, if each xi is closed and I is fine, then the union so closed does the opposite. That is to say, if you have any collection of closed sets and you intersect them, it's still closed. But you can only trust finite unions of closed sets still be closed. Let me see why this is true. I'm going to go quickly to this. To show that that union is still open, you have to show that every X is interior, right? Here. Well, what does it mean for X to be contained in this union? Well, this is like a whole bunch of states. If it's contained in the union, it's gonna live in one of the states, right? Everybody agree with that? And what do we know about each XJ? What's our hypothesis here? They're all open, right? So since X lives in this open set, XJ, it must be an interior point. So there exists delta bigger than zero, such that the neighborhood about X of width delta is contained in XJ, right? But if it's contained in XJ, it's contained in the union of all these. So the union of XI. So yes,
What's the symbol of a J to element of, like, what's that symbol?
this is the index set,
Oh,
right? The index set, so kind of set. Okay, we need to show that a finite union is, so for number two, suppose X1, X2, up to Xn are open. And I think you will see from the proof why we need finiteness. I'll just break this out for my own purposes. But X being the intersection, right? We need to show that there's a neighbor. Well, let me gather my data. X has to live not just in one state, but every state now, right? Because it's an intersection. X has to be an interior, X1's an X1, so it's an interior point. So there's a delta positive such that the neighborhood X delta fits in X1. Do I agree with that? Sorry, Corey, but I'm gonna do all this. Now, what I need to do is I need to find a delta so small that the neighborhood of X of that delta is not just contained in X1, X2, et cetera, it's contained in all of them. Anybody see how I do it? How can I guarantee? So maybe this is a half. I know that a neighborhood of with 1/2 puts you inside X1. Maybe this is a fourth. Neighborhood of 1/4 fits you also in X2. Maybe this is 1/10. Neighborhood of what? With 1/10 fits you into X10. How can I make this fit inside all of them simultaneously? I choose delta sagaciously so that I can fit a neighborhood about X inside all these simultaneously, not just. So for all, delta is less than or equal to delta I, right? Because delta is the minimum of all these. So for any one of these deltas, delta is less than or equal to that, right? And the neighborhood of X, of thickness delta about X is contained in the neighborhood X delta I, right? Because this is just a potentially longer interval, right? This is an interval centered at X with delta. This is centered at X with delta plus 1. So this is inside here, right? Right here. And this is inside Xi. So in X delta is contained in Xi for all I. So the neighborhood of X delta is contained in the intersection of Xi. So the intersection is close. What could potentially happen to my proof if this was an infinite number of sets that I was intersecting? What happens if there's infinitely many? Can somebody explain to me what might happen? How this proof might fail? That's right. So for example, let's suppose that I have infinitely many, countably many of these. And X1, suppose the delta one I need is 1, and then 1/2, and 1/4, and 1/8, and 1/16, and so forth. Suppose it just goes down by a power of 2. There is no minimum. And in fact, we can see that. Here's an example. Let's see, interval from minus 1/n. So X1 minus 1, X2 minus 1/2. What is the intersection? Students forever. It's the intersection. What's that now? Okay, that's a start. 0 is in every one of these, so that's it. And that's it. There can't be anything else. Explain why there can't possibly be anything else. Right, suppose you've got some small value epsilon that's positive that's gonna be in there, right? All you have to do is just find some n such that one over n is smaller than epsilon. Right, and then it'll be, as Mitt says, cut off, right? And that is exactly this Archimedean principle. So whether it's positive or whether it's negative, everything is eventually cut off. So this is 0. This set is not open. Even though every one of these sets is open, this one's not. Because its complement is actually the open set. This one's actually closed. Right? Well, in fact, here's an easy way to see this. This is a single point, so it can't be interior, right? Everybody okay with that? Now, there's still the business about all the closed stuff here. I'm gonna leave 4 for an exercise because I think you can see how this is gonna work. For I want to show the intersection of that is still closed. What does it mean for each of these exercises to be closed? It means closed. Xi complement is, what is the complement of a closed set? Open. So look at the intersection. I hope this is close. Let's see what happens. This is so you use up these laws for useless, right? Everybody agree with that? Xi is Xi complement. Does anybody smell what the rock's cooking? What am I going to do? Uh, How do I go from here to here? Y'all remember proving this earlier with De Morgan's loss of set theory, right? I mean, the intersection of a complement is the complement of the union of the A's. What is this? Exact complement is open. So complement. The union of exact complement is open by number 1. Because the union of a bunch of open sets is open. Right? So when I take the complement of this, these closed. And so there you go. The intersection of a bunch of closed sets still has to be closed. And it's essentially the same thing that we did over there. So see if you can do part 4 yourself. It's not too difficult. We can put a final theorem for today for you all to think about. Oh, and by the way, the math club is perfectly cut out for you guys today because the speaker is speaking about the axiom of choice. And I said, there's some controversial things that come out of this. This is a good one to see because one of the things that comes out of the axiom of choice is the Banach-Tarski paradox, which means I can take my car keys and divide them up into a bunch of finite sets and put it back together and have exactly 2 copies of my car keys of the same material, which is highly non-intuitive. So I'm ready to see that. Here's the last theorem. If A and I real is closed, bounded, and non-empty. I do need non-empty here. Then A contains It's Supreme. At the end of the last section, before we started this, I pointed out to you that, R is a ordered field. And so if you have a bounded set in R, the supremum and infimum is contained in R. The difference of this is, this is true for every subset of R. If it's closed bounded, non-empty, then not only is the supremum and infimum in R, it's actually in set A. So think about that, and we will see folks on Monday.